Yeah, so I'm presenting some work that I've led with a team of PhD students at the University of Reading and Matt Lipson at the Bureau. So it's well known that the impacts of heat waves are exacerbated in cities due to the urban heat island effect. The urban parameterizations in operational forecast models can represent the UHI, with temperatures typically within 1 to 2 degrees of observations. So as you can see here, this paper from Byrne and Stanger et al. So the urban area is about 5 degrees warmer at night, and typically observations sort of within 1 to 2 degrees of the predictions. So to more accurately capture air temperature variability of the city, typically we would use sub-kilometre resolution numeric weather prediction models. However, they're computationally expensive. And we might also further improve our urban parameterizations. However, another potential approach would be to use machine learning because it can be cheaper than going to high resolution NWP. And also, perhaps it might learn these complex processes in urban areas in ways that parameterizations currently don't. So the objective of this study is to provide proof of concept for the use of machine learning to bias correct and downscale UK Met Office operational air temperature forecasts for heat waves in urban areas. So the data in this study will be London, and I'll be focusing on 8 heat waves between 2019 and 2021. And the predictors, so these are the things that the machine learning model will use to predict the air temperature, are the Met Office Operational Limited Area Forecast Model, the UKV. So that uses the Marusis urban scheme and its 1.5 kilometre grid length. And the variables that are available are the net shortwave, cloud fraction, wind speed, relative humidity, sensible heat flux, latent heat flux, ground flux, soil moisture, and hour of day. And we also use this new world cover, land cover data set aggregated to 100 metres. So we also calculated the upstream build fraction. So let's say, take, for example, a point here. We would calculate the land cover fraction upstream of that point at 1 kilometre, 5 kilometre, and 25 kilometre upstream based on the wind direction. So you can see here different land cover types and the fraction 5 kilometre upstream. But in this study, we focused on just using the built up. And the target data set, so that's what we're trying to predict. We've used crowdsourced WOW air temperature observations. So this is a platform maintained by the UK Met Office where citizen scientists can upload their observations. And you can see there's quite good coverage across London. So there's 115 sites after the quality control. And we also used 5 professionally maintained sites, and we held them back purely for testing. This is the machine learning workflow. So we prepared the data, so you've got these variables here that I just discussed. So we put those into the predictor selection hyperparameter tuning, which is an iterative process where after the model training and inference testing, we would go back, update which predictor we wanted to use, and tune our hyperparameters to optimize performance. So as I discussed previously, there's 8 heat waves. So in the training, we would use 7 and test on the 1. So that's like how it would be in reality. We don't have the future. We want to predict the future, and we can only train on the past. And the 1 heat wave we leave out is our future. And then we use 80% of sites and test on 20%. Because we're predicting everywhere, we're making maps. You wouldn't have observations everywhere, so you wouldn't be able to train on all locations. So we used 3 machine learning algorithms, fully connected neural network, MLP, 2 decision tree ones, random forest, and XGBoost. So after that, we made predictions at these sites and compared the predictions to the UKV performance. And then also we made these 100-metre maps of air temperature. So here's the performance, the overall performance for heat waves and the diurnal cycle. So the machine learning algorithms give similar, so about 0.166 on average improvement over the UKV, the operational forecast model. So you can see these here for each of the different algorithms, the difference in root mean square error. And then around the edges, you can see for each heat wave, and you can see there's quite a large variability in the performance between heat waves. So it's important that studies do look at multiple heat waves when they're evaluating their machine learning models. The diurnal profile is much better for the machine learning than the UKV. So in grey is the UKV, black is the observations, the WOW, and in colour are the models. You can see that, it's much closer, the diurnal profile. And the improvements are largest during the day, you can see, and also, interestingly, so we created the UKV forecast by splicing 6-hour forecasts together to create a continuous time series. So with increasing lead time, so between 3 and 9 a.m., you can see that the errors increase for the UKV, but for the machine learning models, they increase less, so it's bias correcting more with increasing lead time. So here's the urban heat island performance. So we're taking the urban minus the vegetated air temperatures from each other. You can see that in the day there's not much, air temperature's about the same, but at night there's about 2.5 degree urban heat island. And in the day, the UKV, the operational forecast model, overpredicts, but the machine learning models can get it much closer. And here on the right is a map using the MLP. You can see what it's doing is it's making the rural area warmer and the urban area cooler. So that overall, that's how we're decreasing the urban heat island. So this is the downscaling bit now. So this is just focusing on this region here. So it's using this land cover data set to downscale from 1.5 kilometers NWP to 100 meters. So there's a general correlation of low urban fractions with lower air temperatures, which is what we qualitatively expect. However, there are some unusual patterns. For example, the River Thames here, it gets warmer as we go east, and there's quite strong temperature gradients in parks, which perhaps we don't expect. So this requires future investigation. So this is the sensitivity to training data amount. So you can see here, as we increase the number of sites, and as we increase the number of heat waves used in training, the root mean square error is still decreasing. It suggests that if we were to go to longer duration observations and including more sites, we get further improvements in machine learning performance. And there are more dense crowdsourced data sets out there, for example, the NetAtmo data set. So then finally, I mentioned we had these professionally maintained sites. So we compared performance, we used the machine learning models at these sites, and we found that machine learning improved over the UKV by approximately sort of 0.05 degrees. So the performance isn't quite as good as at the WOW sites, the crowdsourced sites, but it still improves over the UKV. So you can see this diurnal profile here. So actually, there's in the night and in the morning, the machine learning models are closer than the UKV to the observations, but in the day, there's this warm bias in the machine learning models. So there's potentially several causes of that, but the most probable one is that the crowdsourced data sets have poorer radiation shielding. They have a warm bias in the day, and the machine learning models basically learn this behavior. So then when you compare at the professional sites where they don't have this radiation bias, the machine learning models are over-predicting slightly in the day. But having said that, despite this, the machine learning models are performing still better than the UKV, despite that bias. So in conclusion, we've demonstrated that machine learning models can be used to bias correct the UKV with improvements of approximately 0.17 degrees, and it can downscale the UKV from 1.5 kilometers to 100 meter grid length. So the machine learning models give 3 to 4-fold improvement in the diurnal representation of the urban heat island compared to the UKV, and improvements become large with increasing forecast lead time. And this saying that there is machine learning where your results are only as good as the training data that you use, and this is definitely the case here. So having this crowdsourced data means that we have high density observations in the urban area. That brings benefits for trying to get these high resolution maps and learning relationships with land cover, but there's still issues to overcome for operational modelling, for example, with perhaps biases to radiation shielding. And we can further improve our machine learning models if we have denser, longer duration observations. I'll finish there. Thank you.